Hello, physics students. Today we're going to talk about coordinate systems, velocity, acceleration, and their application to movement and motion in general. Coordinate systems tell you where the 0 point is of the variable you are studying and the direction in which the values for that variable increase. We can apply our Cartesian coordinates as we want to a depiction of motion. We use the coordinate system, the x and y axis, in order to give some order to our inquiry into motion. The origin, or the x and y 0, 0 point, is where the variables have 0 value. If you were to start a measurement of time and distance at this point, both time and distance would be 0. Imagine a track race, a sprint, where the starting line is the beginning point. From this point, we could track motion. One option for tracking motion is a position vector. Vectors will become very important in our inquiry into motion. They are represented by an arrow from the origin to the midpoint of the object. The length of the position vector is proportional to the distance of the object from the origin and to the location of a moving object at a particular time. Vectors represent both magnitude and direction of motion. We will study many different types of vector quantities, including acceleration, velocity, force. In this particular case, we will talk about position, or more specifically, displacement. Vectors, as you know, have two quantities, magnitude and direction, and for the position vector, displacement is the magnitude. Here we see the representation of position vectors in conjunction with the motion diagram that we have studied before. Note that the magnitude is indicated by the length of the red line and the direction of travel by the arrow. Direction. Vectors and scalars. These are two categories that you must be able to distinguish the difference between. A scalar quantity tells you only the magnitude and uses regular variables. For example, m for mass and t for time. Note that time is understood to have only one direction. We do not indicate that it's counting up. M, mass, again, is a quantity of matter, but we appreciate that it is one directional. We aren't having mass in a variety of directions. In contrast, the vector quantities tell you magnitude and direction and have a variable with an arrow above it to indicate that it is a vector quantity. Acceleration is based on a change in velocity and therefore must have direction. Your velocity is directional. We will now begin to compare motion in time. As such, we must acknowledge time intervals in regard to displacement or magnitude of a vector quantity. Displacement defines the distance and direction between two positions. Time interval is the difference between the starting time and the finishing time, and is commonly depicted by the symbol delta t, the triangle referred to as delta, or change, showing a change in time. We must incorporate into our inquiry time as it relates to change. This is our challenge, and it goes beyond many of the applications of mathematics that we have seen up to this point in our academic work. Distance is the position of an object's separation between it and the reference point. It is only a distance. It is a scalar quantity. It is not telling you a direction. D represents the final position, and D sub 0 or D naught is the initial position. Again, when we subtract the initial position from the final position, we will have delta D, the change in the position of an object, and we call this change displacement. When it is directional, it is called displacement. Here we see the notation for the change in distance. Delta D equals D1 minus D naught. Very similar to our time notation. Separation between an object and a reference point is position, using the variable D. The reference point is the zero position from which a measurement is made. We must acknowledge that the displacement of an object is only in relation to its original point. Recall the example from class when we showed that a ruler could be traveled in one direction and another, but only the final direction in reference to the starting position was of significance when we cite position. So if you start at 0, go to 21, back to 17, your displacement is 17. It is your final position relative to your starting point. For a frame of reference, a coordinate system is used to give the movement a relative basis, both in time and distance. It requires direction because it is a vector quantity. Distance is the length or size of a displacement vector, and it is a scalar quantity. When we then augment that distance with a direction, we have the vector displacement. Much of what we're talking about is to distinguish between distance and displacement. One is a subset of the other. Distance is the magnitude of displacement. Displacement is a vector and must have both distance and direction. This all culminates, all these terms come together to give us these final pieces. Displacement, a change of position, delta D. The time interval through which a change occurs, delta T. The final position minus the final time minus the initial time. We put these two together to give ourselves accounting for an average velocity, a change in position divided by time. Delta D divided by delta T is our accounting of velocity. Miles per hour. Kilometers per hour. The per is saying that you are dividing the unit of distance by a unit of time. And as we know, when we use our rates, we have a denominator of 1. We make that convention so that we always will be able to compare to any number of time units, as we have seen in our examples during class. To have another application for velocity is the final equation here on this page, where we show that the initial velocity plus the final velocity divided by 2 will give you an average velocity. You must understand this and use this convention so that you will be able to find an average velocity in your applications and studies. A constant velocity equals the distance covered in equal time periods. Constant velocity is in stark contrast to accelerated velocity. We have seen in our motion diagrams where this is equal distance between dots of the particle model. It must be distinguished from accelerated motion. We have focused extensively on constant velocity using our linear models, and we will soon be moving into accelerated motion using our quadratic formulas. This ends the presentation on acceleration, coordinate systems, and velocity. We will discuss with further examples during class time. Please make time for study and consider all of these various things before it comes to the assessment. Thank you.